Hello and welcome to this video. We're going to be talking about domain and range. This aligns with IXL Pre-Calculus A1. Let's get started. To begin our discussion of domain and range, let's talk about reasonable input and output values. So the table below shows the relationship between the circumference and the height of a tree as it grows. So we can see 1.7 feet to a height of 24.5 feet, so on and so on. You can see the relationship as it grows. And we're going to ask the question, what values make sense for the circumference and height of the tree? For example, does a negative value make sense? Is it possible for there to be a negative circumference? No. So we know our circumference is going to have to be bigger than 0. And I'll let C represent circumference. Similarly with height. Height cannot be negative, so I know height, which I'm going to let be h, also has to be bigger than 0. Now I also know there's got to be an upper limit. This is not going to carry on forever. You can't have a circumference of 1,000,000 or 1,000,000,000, and at some point it's going to stop, and it does. The largest recorded tree has a circumference of 119 feet, or circumference is how big the trunk is. So my circumference is going to have to be less than 119. And similarly for height, no tree is going to be bigger than 376 feet. So this is also going to be less than 376. So now we've defined the input and output values that make sense for this function. Once we have identified the reasonable input and output values, we can then define the domain, which is the set of all possible input values, and the range, which is the reasonable output values, or the set of reasonable output values. So what would be the domain and range of our function of circumference and height? Well, I can write it like this. The circumference is going to be less than 0, greater than 0, because the circumference is not going to be a negative, and less than or equal to 119, because that's the biggest tree on record. And then similarly with height, height is going to be greater than 0 because it won't be negative, and less than or equal to 376, and that defines our domain and range. It can sometimes be tedious to write out all the values of a domain and range of a function, like if it was all positive numbers, 1, 2, 3, so on and so on. You don't want to write all those numbers. So you use a concise notation to simplify things. It's called set builder notation, and it looks like this. You've got curly brackets, then you've got an x, a line, and then a condition, and another curly bracket. So this would read the set of all x such that, this up and down bar means such that, some condition, in this case x is greater than 0. So for our example, circumference and height, we would write it as the set of all c such that c is greater than 0 and c is less than 119. And same thing for height. So this would be the set of all heights such that the height is greater than 0 and less than 376. All right, let's try some practice questions. We're going to determine the domain and range of each of these functions below. Starting with the first one, we've got a radical square root. Now, the square root can never be a negative number. We can't have a -2 or square root of -3. So I know that x minus 4 has to be greater than or equal to 0. Well, that just means x has to be greater than or equal to 4. So I can right away define my domain. X, the set of all x such that x is greater than or equal to 4. Now, the lowest value that the range can be, keeping in mind that it has to be positive, is going to be when x is 4. 4 minus 4 is 0, and the square root of 0 is 0. So the range is going to be set of all y such that y is greater than or equal to 0. On this next one, we're dealing with an exponential. Now, it is always the case that with an exponential, the domain is all real numbers. You can put any number in for the domain. It can be a fraction, a decimal, a negative number, anything. And this is always true. So you can count on that one. Now the range is actually going to be based on, if we look at the form of the equation, a times bx plus some number out here, c, this number is going to determine what the range is. In this case, our number out there is just 0. So our range is going to be the set of all y such that y is greater than but not equal to 0, because if we look at the graph, it's going to get really close to y equals 0, but it's never going to touch it. So that's why it's greater than. Let's try the last one. In the last one, we're dealing with a logarithm. Now the input of logarithm can never be negative. So I know that my x is going to be the set of x such that it's greater than 0 and not equal to 0. The range, however, for logarithms is always all real numbers. I'm just going to write hashtag all real numbers. And this is true always. Just like the domain of exponential is always all real numbers, the range of logarithm is also always all real numbers. And the domain of a logarithm, the range of a logarithm is always all real numbers. And the domain of a logarithm is based on whatever is on the inside, the x here in this case. All right, same thing, determine domain and range, but this time we're given a graph. Now, look at this first one. This is going to be an exponential function, something of the form a times b to the x. Keep in mind, it's approaching 0, but not actually touching it. So I know, because it's exponential, x is going to be the set of all real numbers. I'm just going to write the hashtag. And the range is going to be greater than 0, but not equal to. This next one is an absolute value function of the form like this. It's shifted down to -5, but my input is going to be all real numbers because it goes to left and right in either direction, and you can put anything in for the absolute value. So x is going to be all real numbers. And your y is going to be anything bigger than -5. So y such that y is greater than and also equal to -5. So that's it for this lesson. Now go and try some practice on your own.